So far, we've only known about 2 interstellar visitors in our recorded history. That is, until now, because astronomers have just detected another something out there blazing into our solar system at like 152,000 miles an hour.
When NASA directed its instruments toward the interstellar object known as 3Y Atlas, few expected that the real breakthrough would come not from telescopes or spacecraft, but from an unexpected collaboration with Google's artificial intelligence. 3I Atlas, only the third interstellar body ever confirmed to have passed through our solar system, carried with it a wealth of unprocessed data: light curves, spectral signatures, motion trajectories, and chemical traces hidden in fleeting observations. NASA, overwhelmed by the sheer density of the raw information and aware of the complexities of interstellar material, made the decision to feed the entire dataset into Google's advanced AI systems. What emerged from that effort shocked scientists in ways they had not anticipated, altering not only how humanity viewed this specific visitor from beyond, but also how artificial intelligence could reframe the practice of astrophysics itself. Before we start, smash the like and subscribe buttons for more updates. The object, detected rushing through the outer solar system at incredible speeds, had already been noted for its peculiar trajectory. Unlike comets or asteroids bound to the gravitational well of the Sun, 3Y Atlas traced a hyperbolic path, marking it as an unmistakable outsider. Its surface glimmered differently than expected under spectroscopic analysis, producing spectral lines that didn't neatly match the catalog of known materials. Astronomers logged terabytes of observations in a matter of weeks, yet even after preliminary analysis, much of the data sat locked in a complex lattice of variables too dense for human teams to process with ease. NASA's partnership with Google provided an opportunity to turn over this extraordinary trove to an AI model capable of identifying patterns invisible to human eyes. Once the AI began parsing the data, it was not simple recognition or classification at play. Google's algorithms reconstructed missing data points, corrected observational noise, and generated simulations of how 3I Atlas might have formed and evolved before crossing into the solar system. What stunned scientists most was that the AI did not simply confirm theories they already held. Instead, it suggested material compositions and energy signatures that hinted at chemistries not native to our local stellar neighborhood. These results implied that the object had been forged in conditions unlike those present in the Milky Way regions astronomers typically study, raising the prospect that interstellar objects can act as couriers of cosmic diversity. The implications stretched far beyond the technical marvel of machine learning applied to astrophysics. If 3I Atlas carried with it traces of elements or compounds rarely encountered near Earth, then each interstellar visitor represented a natural probe, a fragment of alien star systems traversing our skies. The AI identified anomalies in its reflective spectrum that suggested highly complex organic molecules, ones that might have formed under environments richer in radiation or subject to stellar winds harsher than those in our system. For researchers long intrigued by panspermia, the hypothesis that life's precursors might travel between stars carried on comets or rocks, this result was tantalizing. NASA's scientists suddenly found themselves considering whether interstellar objects like 3I Atlas might seed star systems with the basic chemistry necessary for biology. Equally important was the methodological leap. Traditionally, data analysis in astronomy had relied upon long cycles of human interpretation, with models refined slowly as new data trickled in. Feeding 3I Atlas's information into Google's AI flipped that paradigm. Within days, the system produced correlations that teams of astronomers might have required years to assemble. The AI linked faint emissions in one wavelength to subtle variances in trajectory, showing how sublimation of exotic ices influenced its flight path. By automating the connections, it revealed the holistic story of the object's journey, a narrative that no single scientist could have pieced together from fragments alone. For NASA, this was not merely a matter of speeding up calculations. It was a reorientation of scientific labor. Researchers now saw AI not as a tool to simply crunch numbers, but as a partner capable of intuition-like leaps across datasets. The discovery that 3I Atlas harbored materials with unearthly origins was less shocking than the realization that such a conclusion might never have been reached through traditional methods. Human teams, bounded by existing assumptions and frameworks, often filter data through what they expect to find. The AI, unconcerned with expectation, unveiled possibilities no one dared hypothesize. The shock reverberated in conference rooms and laboratories. What if countless prior datasets archived for decades contained overlooked signals because human analysts assumed they were noise? What if entire generations of astronomical discoveries lay dormant, hidden not by distance or faintness, but by the limitations of human perception? 3. iAtlas's revelations became a wake-up call that the future of space science might hinge not only on building better telescopes, but also on creating better intelligences to interpret what those instruments capture. NASA's decision also underscored the necessity of interdisciplinary collaboration. Astrophysicists, planetary scientists, and chemists suddenly found themselves in dialogue with computer scientists and engineers. Google's AI was not just an analytical engine. It was a conceptual bridge, merging the observational rigor of astronomy with the inferential power of machine learning. By working together, these teams began to see 3Y Atlas not only as an interstellar rock, but as a key to testing grand cosmological theories. Its trajectory, its chemistry, and its very presence in our solar system could inform debates about how matter circulates between stars, how galaxies exchange material, and how systems evolve over cosmic time. The object itself became almost secondary to the methodology it inspired, but scientists could not ignore the startling specifics the AI revealed. The chemical anomalies it highlighted pointed to isotopic ratios not typically found in local star-forming regions. This suggested that 3Y Atlas originated in a stellar nursery markedly different from those near Earth, perhaps from a system with higher metallicity or one shaped by more violent supernovae. Its path, once thought to be a simple hyperbolic escape, contained micro-perturbations that hinted at encounters with massive bodies long before it reached us. A cosmic breadcrumb trail reconstructible only through AI's relentless pattern recognition. As the AI extrapolated backward, it produced models of 3Y Atlas's possible birthplace. Scientists watched in astonishment as simulated star maps emerged, narrowing potential regions of origin based on chemical signatures and trajectory reconstructions. The possibility that we could trace an interstellar wanderer back to its native star system was once science fiction. Now it stood as a plausible scientific endeavor. Suddenly, 3I Atlas was not just a passing object, but a messenger carrying the imprint of its home galaxy. The impact on scientific imagination was profound. Discussions erupted about whether interstellar objects might serve as natural messengers of intelligence-free communication. If 3I Atlas could carry chemical blueprints of distant stars, could other objects, larger, older, more complex, transport signatures of biological processes? Some began to envision a cosmic archive traveling invisibly between stars, with each object a page in a vast interstellar library. In this vision, artificial intelligence becomes the reader, capable of deciphering what humans cannot. The collaboration also pushed forward the ethics of AI in science. By relying on machine learning to interpret fundamental astronomical data, scientists confronted the reality that their understanding might increasingly be mediated by systems they could not fully explain. The AI's conclusions about 3Y Atlas were statistically robust, but the pathways it took to reach them were often opaque. Researchers faced the paradox of possessing answers without always knowing the precise reasoning, a challenge to the very philosophy of science. Still, the accuracy of its predictions and the novelty of its findings forced acceptance that the frontier of knowledge might depend on trusting intelligences that operate beyond human intuition. In this way, 3I Atlas became more than a cosmic traveler. It became the pivot point for a transformation in how humanity approaches the unknown. Scientists were stunned not merely by what was discovered about the object, but by how it was discovered. The shock was as much existential as it was empirical. For centuries, astronomy had been about sharpening human senses, extending vision through telescopes, extending hearing through radio dishes. Now, with AI, a new sense had been added, one not bound to human cognition. The event unfolded almost like a parable of the future. A rock from another star passed through our neighborhood, carrying secrets older than the Earth. Humans, armed with their machines, captured its fleeting signals but could not make sense of them. Only by turning to another intelligence, one born not of nature but of mathematics and silicon, were those secrets revealed. The result was an expansion of perspective. a reminder that in the grand scale of the cosmos, even our methods of knowing must evolve. As more interstellar objects are inevitably discovered in the coming decades, the precedent set by 3Y Atlas will shape the protocols of exploration. No longer will such visitors be treated as curiosities analyzed in isolation. Instead, they will be seen as opportunities for collaboration between human ingenuity and artificial cognition. The shock that accompanied NASA's use of Google's AI was not simply that something new was learned, but that it suggested an entirely new pathway for learning itself. The implications ripple outward into every corner of scientific thought. If AI can reveal the hidden stories of interstellar objects, could it not also decode the faint signals of distant exoplanet atmospheres? Could it find patterns in cosmic microwave background fluctuations that elude even the most skilled cosmologists? 3I Atlas's data became the test case, the proof that the limits of discovery are not set by the universe, but by the tools we use to interpret it. In the wake of this event, laboratories buzzed with anticipation of applying similar methods to archived datasets. Observations from decades past, once dismissed as inconclusive, could be revisited with fresh eyes, not human, but artificial. Entire catalogs of comets, asteroids, and stellar observations might contain secrets waiting for an AI to uncover. 3I Atlas's fleeting passage thus became the seed for a revolution in the way humanity minds its own scientific history. The story of 3I Atlas and Google's AI is not about a single discovery, but about a moment of realization. For the first time, humanity glimpsed the potential of combining interstellar messengers with artificial interpreters. The shock that scientists felt was not fear but awe, a recognition that we stand at the beginning of a new epoch, where the mysteries of the cosmos may be unraveled not solely by human minds, but by minds we have created to walk beside us. The revelations drawn from the AI's analysis of 3I Atlas quickly became more than a collection of extraordinary findings. They became a demonstration of how human curiosity, when amplified by machine intelligence, could peel back layers of the universe that had remained hidden for eons. The scientists who watched these results emerge were not only startled by the novelty of the data, but also by the sheer scope of what it suggested. Each piece of information hinted at a far-reaching network of possibilities: interstellar travel of materials, galactic chemical exchanges, and the deep interconnection between star systems that until now had only been theoretical musings. The deeper the AI examined the information, the more it revealed dimensions of 3I Atlas that human teams had overlooked. The object's rotation, for instance, had been poorly constrained when analyzed by traditional methods. The irregular flickering in its brightness had been assumed to be observational noise. Yet the AI highlighted correlations between this flickering and subtle thermal signatures, ultimately concluding that 3I Atlas rotated in a chaotic tumbling motion rather than a stable spin. This detail, minor at first glance, opened pathways to understanding how the object might have endured collisions or gravitational slingshots during its interstellar journey. A tumbling rotation implied a violent past, one marked by interactions with bodies massive enough to alter its spin. The AI also suggested that this chaotic motion contributed to unusual outgassing patterns observed in its trajectory. Instead of evenly shedding volatile materials, 3Y Atlas released them sporadically, causing small but measurable course deviations. Human scientists had noted the anomalies but struggled to attribute them to specific mechanisms. By combining the physics of rotational dynamics with the chemistry of sublimation, the AI recreated a model of the object's motion that explained the observed path with unprecedented accuracy. For NASA's teams, this wasn't just a correction of a minor error. It demonstrated that AI could weave together physics, chemistry, and observational data into a coherent synthesis that extended beyond any single discipline. Beyond its physical behavior, the object's chemical mysteries continued to astound. The AI identified isotopic ratios, specifically in oxygen and carbon, that were distinctly foreign when compared to known solar system materials. These ratios hinted that 3Y Atlas might have originated from a star-forming region where the balance of stellar nucleosynthesis had been shaped by supernova or cosmic ray bombardment unlike anything seen nearby. The implication was staggering. Every interstellar object could represent a fingerprint of the galactic environment it once called home. With enough such samples, humanity could build a map of galactic chemistry, tracing how matter evolves across light years and ages. This prospect filled scientists with a sense of awe. For centuries, humans had studied the cosmos by looking outward, peering at distant stars and galaxies with instruments that stretched the limits of perception. Now, for the first time, pieces of those distant places were coming to us, delivering themselves into the solar system like ancient letters arriving in a cosmic mailbox. And with the help of AI, humans could finally read them. 3I Atlas was not just a stray rock, but a messenger carrying the handwriting of another part of the galaxy. The AI's capacity to reconstruct possible origins for the object also pushed scientific imagination into new territory. By backtracking its path through space, accounting for perturbations along the way, the AI generated candidate star systems where 3I Atlas might have once resided. Though not precise enough to single out one system, the narrowing of possibilities gave astronomers a target list. Telescopes could now survey those regions with heightened interest, seeking stars of the right age, composition, and environment to match the object's properties. This convergence of AI-driven analysis and observational astronomy suggested a future where every interstellar object could serve as a breadcrumb leading back to unknown corners of the galaxy. In this pursuit, the shock was not confined to the astrophysical community. Planetary scientists began to wonder whether interstellar visitors like 3I Atlas could play a role in delivering exotic chemistry to developing planetary systems. If even one such object collided with a young world, it could seed that planet with compounds never before present in its environment. This possibility added a new dimension to the story of planetary formation and the origins of life. Suddenly, the exchange of matter between stars seemed not only plausible but potentially common, turning the galaxy into a vast web of chemical and biological exchange. The philosophical consequences were equally profound. For generations, the question of whether humanity was alone in the universe had centered on the search for distant signals or habitable planets. Now a new angle emerged. Perhaps the building blocks of life did not stay confined to one star system, but roamed freely across the galaxy, hitching rides on objects like 3I Atlas. If so, then life might not be an isolated phenomenon, but an emergent property of galactic chemistry itself. The AI had not discovered life, but by uncovering new chemical signatures, it had expanded the frame of what was possible. For NASA, the event also underscored a new kind of responsibility. If AI could so dramatically reframe the interpretation of interstellar data, then every future discovery would need to be approached with both rigor and caution. Researchers realized that feeding raw datasets into AI was not simply a shortcut to analysis, but a transformative act that could shift paradigms. The shock of 3I Atlas lay not only in what was uncovered, but in the recognition that scientific revolutions might now emerge not from new telescopes or missions, but from reinterpreting existing data with more advanced intelligences. As discussions deepened, scientists recognized another implication: the possibility of applying similar techniques to data collected from long-past missions. The archives of space agencies are vast, filled with raw observations from probes, telescopes, and satellites that had never been fully parsed. What if the Voyager records of interstellar plasma contained overlooked anomalies? What if comet samples collected decades ago carried unnoticed traces of unusual isotopes? The AI's success with 3I Atlas turned these what-ifs into urgent opportunities. The culture of science itself began to feel the tremors of this shift. Traditionally, breakthroughs had come from rare individuals, geniuses whose insights illuminated hidden truths. Now, the genius appeared not as a single person, but as a system, an intelligence designed to recognize patterns at scales humans could never match. While some resisted, worried about diminishing human creativity, others embraced it, seeing the partnership as an expansion of what humanity could achieve. The case of 3I Atlas was a reminder that the cosmos itself was not changing. What had changed was our capacity to listen and understand. The very notion of exploration took on a new flavor. For centuries, exploration meant sailing outward, extending presence into uncharted territories. But with 3I Atlas, exploration meant something different, letting the universe come to us and equipping ourselves with the tools to decode its language. The event suggested that humanity's role in the cosmos was not limited to reaching other stars, but also to interpreting the gifts those stars occasionally sent our way. As more details poured from the AI's processing, further surprises emerged. Thermal models suggested that 3I Atlas contained materials that sublimated at unusually high temperatures, unlike typical ices found in comets. This raised the possibility that it had formed in a region closer to its original star, enduring intense radiation before being ejected into interstellar space. Such an origin story aligned with violent planetary migrations or close stellar encounters, scenarios that shaped its trajectory long before it arrived near Earth. Each detail added to the portrait of an object that had lived a dramatic life, surviving chaos to finally drift into our system. What startled scientists most was how the AI's models gave the object an almost narrative quality. By stitching together clues from disparate datasets, it presented a coherent story of birth, transformation, and exile. This storytelling capacity blurred the line between analysis and imagination, suggesting that AI could act not just as a calculator but as a cosmic historian, reconstructing tales that would otherwise remain untold. The broader scientific community quickly recognized the significance of this new role. If 3I Atlas could have its biography written by an artificial intelligence, then so too could every star, planet, and object in the archives of observation. The universe itself became an open book, and AI offered the language in which to read it. This sense of narrative shocked researchers because it reshaped their relationship to data. No longer were they passive observers of numbers and signals. They were interpreters of stories told by machines about the cosmos. As word spread about the analysis, other disciplines outside astronomy took notice. Geologists wondered whether AI could reinterpret Earth's oldest rock samples in the same way, uncovering overlooked isotopic traces of early planetary processes. Biologists speculated on whether the recognition of complex organic signatures in space might inform their search for life's earliest chemical ancestors. Even philosophers joined the conversation, asking whether AI's capacity to reveal unseen truths suggested a new way of knowing, one that humans alone could not achieve. The shock of the event resided not just in the scientific implications, but in the cultural reverberations. The story of a rock from another star, analyzed by an artificial mind, captured imaginations worldwide. For the public, it symbolized a new era of exploration, one in which discovery was not confined to astronauts venturing into space, but expanded to collaborations between human ingenuity and artificial cognition. 3I Atlas became a symbol of a future where humanity's reach was extended not only physically, but intellectually, through tools capable of seeing what eyes and minds alone could not. As NASA and Google reflected on the achievement, they recognized the potential for this collaboration to become a template for future endeavors. Interstellar objects were rare but not unique, and more would certainly follow. By preparing AI frameworks ahead of time, scientists could ensure that the fleeting windows of observation were maximally exploited. Unlike human teams, which could take months or years to process data, AI could deliver insights while the object was still observable, guiding telescopes in real time to focus on the most promising features. The experience also highlighted the importance of trust. While scientists were stunned by the revelations, they also faced the challenge of verifying AI's conclusions. Independent checks and repeat observations were essential to ensure accuracy. Yet, as each layer of analysis confirmed the AI's findings, confidence grew. The shock transitioned from disbelief to acceptance, cementing the role of AI as an indispensable partner in unraveling cosmic mysteries. When the flow of results from the AI analysis began to settle into the hands of researchers, what struck many was how much of the universe's subtle complexity had been hiding in plain sight. The 3I Atlas dataset was not unusual in terms of structure. Astronomers had collected similar swaths of raw light curves and spectral signatures before. Yet the difference was in what the machine learning system chose to prioritize. By layering correlations between elements of the data that human scientists often treated as separate, it built bridges across disciplines that had long worked in silos. For the first time, thermal behavior was not analyzed independently of compositional data, and trajectory was not studied in isolation from internal chemistry. Everything connected. This realization triggered a reassessment of how science itself had been conducted for decades. The division of labor in astrophysics, where one group studied dynamics, another chemistry, and yet another spectroscopy, had always been practical, but also limiting. AI obliterated those walls by treating every data point as part of a single system. In doing so, it produced insights that were not merely deeper, but more holistic. For 3I Atlas, this interconnected approach meant understanding the object not as a collection of numbers, but as a living process, shaped across billions of years, carrying the fingerprint of cosmic events that stretched back before Earth even existed. The AI also forced researchers to confront the limits of human bias in interpretation. When analyzing data, humans often gravitate toward explanations that fit established models. But with 3I Atlas, the AI flagged anomalous readings that human analysts might have discarded as errors. Among these anomalies were faint absorption lines that hinted at complex carbon structures. At first, skepticism ran high. Could such molecules exist in the harsh environment of interstellar space? Yet repeated simulations confirmed their plausibility. In overlooking these faint signals, humans had almost missed one of the object's most important features: its potential as a carrier of prebiotic chemistry. This discovery carried implications for astrobiology. If interstellar objects routinely carry such molecular complexity, then the galaxy might be teeming with seeds of chemistry that, under the right conditions, could flourish into biology. Scientists began reimagining the story of life's emergence not as a closed system within one solar system, but as a galactic-scale phenomenon where chemistry drifts between stars, collides with young worlds, and provides the raw toolkit for biology to arise. 3. Atlas, in this framing, was less a curiosity and more a messenger of galactic connectivity, a fragment of proof that life's ingredients are not confined to a single corner of the cosmos. In addition to chemistry, the AI's analysis of structural density patterns raised questions about the very nature of interstellar object formation. While most solar system comets are relatively porous, 3I Atlas displayed regions of anomalous density, pockets where matter seemed compressed far more tightly than expected. The AI suggested that these dense zones might have originated from shockwave interactions, possibly from supernova remnants or intense stellar winds in its birth region. If accurate, this meant the object carried within it a geological record of violent astrophysical processes, preserved like a fossil of cosmic turbulence. The excitement these findings generated stemmed from their broader applications. If interstellar objects preserve snapshots of their environments of origin, then studying them offers a direct way to sample distant regions of the galaxy without ever leaving home. Instead of launching probes to other stars, a feat still centuries away with current technology, humanity could use visiting interstellar objects as natural couriers, each one a data capsule of alien stellar neighborhoods. 3I Atlas was simply the first to be so deeply unwrapped, but it would not be the last. The AI also transformed how scientists thought about observation windows. Normally, the fleeting passage of such an object would limit the amount of knowledge extracted. But because AI could rapidly digest raw inputs and generate simulations in near real time, telescopes could be directed more effectively while the object was still visible. This dynamic feedback loop between observation and analysis represented a revolution in methodology. With 3I Atlas, telescopes could chase signals flagged by the AI, confirming or refining predictions before the object receded beyond detection. This kind of adaptive science, driven by a dialogue between machine analysis and human oversight, had never before been possible. While many celebrated, others quietly marveled at the philosophical turn such events represented. The cosmos, once perceived as remote and incomprehensible, now seemed slightly more intimate. A distant star's chemistry had journeyed here, into the cradle of our solar system, and an intelligence of our own making had revealed its secrets. It was a humbling reminder that the universe was not a distant abstraction but an active participant, delivering messages when we were ready to decode them. In academic halls, discussions soon turned to what this meant for the future of discovery. If AI could reconstruct 3I Atlas's story, then could it not also apply similar techniques to the hunt for exoplanets? The challenge of detecting subtle chemical signatures in exoplanet atmospheres mirrors the difficulties of parsing faint signals in interstellar objects. With AI, faint absorption lines that once disappeared into noise could become legible clues pointing to water vapor, methane, or even biosignatures. The methodology tested on 3I Atlas might one day be the very process that confirms life on a distant world. The implications reached even further. Cosmologists speculated that applying AI to large-scale survey data might reveal patterns in galactic evolution or dark matter distributions that humans had overlooked. Particle physicists wondered if data from cosmic rays could yield unexpected relationships when processed with similar systems. In this sense, 3I Atlas served as a proof of principle not just for astrophysics, but for science itself. When machines collaborate with human curiosity, the universe speaks in new tones. The societal response mirrored this excitement. Beyond the laboratories, ordinary people were captivated by the notion that a traveler from another star had entered the solar system and that its secrets had been unlocked by artificial intelligence. Media outlets portrayed it as a story of partnership between humanity and its creations, a glimpse of how technology could extend not just human reach, but human understanding. For many, it felt like a turning point in the narrative of exploration. Humanity was no longer alone in seeking meaning from the cosmos, but had enlisted allies of its own design. In classrooms, educators began reworking their curricula to include discussions of AI-driven discovery. Students were invited to imagine futures where their role as scientists would not be to manually sift through data, but to guide, interpret, and refine the insights of intelligent systems. The shock of 3I Atlas thus seeded a cultural change, preparing a new generation to think of AI not as a competitor, but as a collaborator in the grand pursuit of knowledge. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA feeding 3I Atlas data into Google AI? We want to hear from you. Thank you for watching, and see you next time.